Welcome to the chemistry crash course. Today we are going to discuss about the spectrum of the hydrogen atom. In our last class we discussed about the spectrum, solar spectrum, atomic spectrum. Okay. So today we are discussing about the spectrum of the hydrogen atom. And here when the hydrogen gas is passed through a discharge tube under lower pressure, it will going to emit a light, and that light or radiation is analyzed through the prism. We are going to get the different lines arranged in different regions. Okay. And these lines are categorized into 5 categories, that is Lyman series, Bohr series, Paschen series, bracket series and Fund series. Okay. So all these are the 5 series of the hydrogen spectrum. 5 series of the hydrogen spectrum. How these lines are obtained? See here, whenever the energy level, suppose this is the first energy level, let me draw the some diagram. This is n is equals to 1 and this is n is equals to 2, n is equals to 3, n is equals to 4 and 5, so on. Okay. So like this, whenever in an atom nucleus is present and electrons are revolving around it in the orbits. Okay. So until and unless the electron is revolving in this orbit, it will not going to be jump from this orbit to another. That energy level is stationary, we can say. And then whenever I am providing some sort of the energy to this electron, means it can able to jump from its orbit to the next orbit. Okay. So when it gains the energy, it will going to jump from its orbit to the next orbit, and after some time again this electron jumps to the previous level by emitting certain radiation, and this radiation occurs in the form of lines. That is nothing but line spectrum of the hydrogen, and those lines are categorized into 5 series: Lyman, Bohr, Paschen, bracket and Fund. Okay. See here how these are formed. Suppose the radiations are coming from higher energy level to the first energy level, from higher energy level to the first energy level, that will going to form the Lyman series like this. The radiations are coming to the n is equal to 1, that is the first energy level from the higher energy level. This series is known as Lyman series. This series is known as Lyman series. Here the value of the n1 is 1 while n2 is 2, 3 like this. Okay. So higher energy level means the first one will be the first level will be the n1 value, and the higher level means 2, 3, 4, 5, so on. Like this we can give the explanation for the Lyman series, and Lyman series is present in the ultraviolet region. Okay. So this is regarding the Lyman. Suppose the higher energy level radiations are jumping to the second energy level, that is n is equals to 2, and it will going to give us Bohr. It will going to give us Bohr series. Okay. And this Bohr series is available in the visible region, and then the value of the n1 for the Bohr series is 2, and the value of the n2 will be 3, 4, 5, because for the second level the radiations are coming from where those are coming from 3, 4, 5 and so on. Okay. So this is how Bohr, and similarly if it is come for the third, that acts as a Paschen. If it is for fourth energy level, that is the bracket. If it is the fifth energy level, that is the Fund series. Okay. So these 3 series, that is the Paschen, bracket and Fund series, are those will be in the infrared region. Infrared region, those are available. And these n1 and n2 values are very important. Okay. And then in order to calculate the wave number of these lines, we have the formula that we know that wave number nu bar is equals to 1 by lambda, and then which is equals to r into 1 by n1 square minus 1 by n2 square, and here R is called as Rydberg constant. R is called as Rydberg constant, and this equation is known as Rydberg equation. Okay, and then the value of the R will be that is given here in terms of the centimeter, and keep in mind that N1 and N2 are the integers, always N2 is greater than N1. See here, always in all the series N2 is greater than the N1 value. So in order to find out the wave number of the any spectral line of the hydrogen atom, we are using the Rydberg equation. The equation is that nu bar is equals to 1 by lambda, that is equals to R into 1 by N1 square minus 1 by N2 square, where R is the Rydberg constant and N1 and N2 are the integers. N2 is always greater than N1. Okay, so this is how we can explain the line spectrum of the hydrogen atom. Clear? So next we will go for the Bohr model of an atom. Scientist Niels Bohr proposed a model which is in order to tell some ideas regarding the atoms. Okay, the first one, what is that? Bohr's model first postulate is that the electrons are revolving. For example, let us take, not example, let us take here the structure. This is the nucleus, and here the electrons are revolving around it. Okay. The electrons will going to revolve around the nucleus in certain selected circular orbits, and these orbits are having the definite energy. These orbits are having the definite energy, and these are called as energy levels or energy cells, and those are named as K, L, M, N and so on. Okay. So the electron will going to revolve around the nucleus in certain selected circular paths, and these paths are called as orbits or energy cells or energy levels. Okay, this is the first postulate of the Bohr model. And next one, as long as the electron revolve, in that particular orbit, it will not going to that it consisting of the definite amount of the energy. It will not going to lose the energy, or it will not going to, during that time the energy is constant. That is what we called as, these states are stationary states. These are electrons are revolving in the circular orbits, so those are stationary because the energy, the electron is associated with a definite amount of the energy in this orbit. Okay, and then one more third point, the angular momentum of the revolving electron is an integral multiple of the h upon 2 pi. See here, this h upon 2 pi. This is the angular momentum of a electron, which is always an integral multiple of h upon 2 pi value. Okay, and the electron jumps from higher energy level to the lower energy level, when it loses the energy, or it will going to jump from lower to higher energy when it gains the energy. Okay, and then we can say that suppose E1 and E2 are the energy levels. Okay, let us consider the first energy level. This is E1 and this is E2. Suppose the electron is jumping from E1 to E2, it means lower to higher. It requires the energy. It will going to gain the energy. Suppose this electron which is from E2, higher energy level, it is jumping to the E1, lower energy level. It will going to emit the energy. This energy difference is given by delta E is equals to E2 minus E1. Clear? So this is how we can tell the postulates of the Bohr's atomic model. So next, according to Bohr's atomic model, the energy of an electron, in the nth orbit, En is equals to minus 2 pi square m into e raised to 4 z square divided by n square into h square. So when we substituted the value of the mass charge of the electron, we are substituting all the values, the energy of the electron in the nth orbit will be this much. That is, it is expressed z and n, these values, these are kept as it is, and all other h value, m value, pi value, e value they have substituted and they have calculated it. It is the value we are getting here in terms of kilojoule per mole. Suppose if this kilojoule per mole is converted in terms of electron volt per atom, we are going to get minus 13.6 into z square divided by n square as our formula. So, these are the formulas which are very important in order to calculate energy of the electron in the nth orbit. Okay. So, this is expressed in terms of kilojoule per mole, while this one is when the energy is expressed in terms of the electron volt. Clear? Next, one more expression, the radius of the orbit. The radius of the orbit, as you know, this is the orbit. This is the nucleus and this is the electron, this is the orbit. The radius of this orbit expression is given n square h square divided by 4 pi square m into z into e square. Okay. And then velocity of the electron in the nth orbit is given by n into h divided by 2 pi into m into r. So, when they have substituted the value of the this all, we know the value of radius, we know the value of the radius, substitute the value of the radius here and simplify it. Finally, you are going to get the velocity of an electron in the nth orbit is 2.19 into 10 to the power 6 into z divided by n meter per second. Clear? So, these are the formulas which you need to know and you need to remember also. Next, photoelectric effect. See here, photoelectric effect was observed by the scientist Einstein, and here what is the photoelectric effect? Let us consider this as a metal surface and some radiation is fallen on this metal surface, so that the electrons from the metal surface will going to be ejected. It will going to be ejected. That process is called as photoelectric effect. So, what is the meaning of the photoelectric effect? Photoelectric effect is ejection of the electrons from the metal surface when the suitable frequency of radiation is fallen on it. When the suitable frequency of the radiation is fallen on it, that process is called as photoelectric effect. Okay. So, few more points which are very important here. See here, whatever the radiation which is fallen on the metal surface, those cannot able to eject the electron. Then which type of the radiation? The minimum frequency of the radiation is needed. Whatever the radiation is falling on the metal surface, that must possess a minimum frequency in order to eject the electron. That minimum frequency which is capable of ejecting the electron from the metal surface is called as threshold frequency. If the radiation is having less frequency, that is less frequency than that of the threshold, means there is no ejection. There is no ejection. Compulsory, there must be a minimum frequency of the incident radiation that must be capable of eject the electron from the metal surface, and that minimum frequency is called as threshold frequency. Okay. And then here few more points. The number of the electrons ejected, the number of the electrons which are ejected here, those depends upon the intensity of the incident radiation. That depends upon the intensity of the incident radiation. And one more thing, the kinetic energy is directly proportional to the frequency. The kinetic energy of the electron is directly proportional to the frequency of the incident radiation. So, these are the experimental observations of the photoelectric effect. The definition is we are getting the electron ejection from the metal surface when the suitable frequency is fallen on it, and these are the experimental observation. First one is regarding threshold frequency, next one is how many number of electrons, so those depends upon the intensity, and the kinetic energy depends upon the frequency. It means it is directly related with the frequency. Clear? So last one more theory is there, that is the Planck's quantum theory. Here the energy is emitted or absorbed discontinuously in the form of small packets of energy called as quanta. The energy is emitted or absorbed discontinuously in the small packets of the energy. Those packets of energy is called as quanta. Okay. And then here the energy is directly proportional to the frequency. The Planck's quantum theory indicates the particle nature of the light, particle nature, okay, and then the energy is directly proportional to nu, and this directly proportionality constant is removed and one more constant is added, h, that is E is equals to h nu, where h is the Planck's constant and which is having the value of 6.62 into 10 to the power minus 34 joules. Okay. And here also the energy is the integral multiple, energy is the integral multiple of h nu quantity, energy is the integral multiple of the h nu quantity. And one more point they have observed here, the kinetic energy, that is Ke, kinetic energy half mv square is equals to h nu minus h nu naught. This is the threshold frequency and this is the frequency. Okay. So these are the points which are covered from the Planck's quantum theory. First one is the energy emitted or absorbed discontinuously in the form of small packets of energy called as quanta, and energy is directly proportional to the frequency, and this is removed by one more constant h, where h is called as Planck's constant, whose value is 6.626 into 10 to the power minus 34 joules, and energy is always an integral multiple of h nu quantity. And finally kinetic energy is equals to h nu minus h nu naught. Okay. So all these are the concepts which are very important, and the questions will be asked on this, and we are going to solve some questions in our next class. Okay. Thank you.